All right, so in this video, we're going to look at how to use the calculate probabilities with the normal distribution in the TI-83 and 84. So we're going to look at calculating probabilities between two values. Now, it is worth noting that the TI actually does by default specifying two values, as opposed to traditional ways of calculating the normal distribution will always be just less than a single value. So if you're switching from one application to another, this is worth keeping in mind. If you're using, for instance, Excel or some other statistical tool, they usually will just do less than something and not in between two things. So this is a little different. Now, in order to get to the normal distribution function, we are going to get into the distribution menu. So we're going to press second and then the vars key. So again, the vars key is the third one down on your screen. It is the second over from the left, right next to the clear button, or sorry, second over from the right next to the clear button. You'll see it has distribution above it. So second vars will get you to distributions, and then you will scroll down to get the normal CDF. Now, one thing to kind of keep in mind is the normal PDF we only use for graphing. This is a continuous probability distribution. And so the PDF doesn't actually calculate probabilities for us. It essentially is calculating just the height of the distribution. So when we're calculating probabilities, we never, ever, ever use the normal PDF. For discrete distributions like the binomial, we do use both the PDF and the CDF, and we need to know when to use it. But for the continuous distributions, like the normal distribution, never, ever, ever calculate probabilities using the PDF because they will be wrong. So always the CDF. Now, what we're going to have to specify is an upper bound and a lower bound in the order lower first, then upper. Then we're also going to have to specify then the mean and the standard deviation. Now, in the classic mode, you would then have to separate all of these by commas. If you're using the stats wizard mode, then you'll get a list on the screen of what to put where. So after you select the normal distribution, let's go through and do an example. Now, suppose that I want to calculate the probability that my z-score is less than 1.35. Now, the z-score is telling us that the mean is 0 and the standard deviation is 1. This is from a standard normal distribution. So this has either been converted to a z-score or we're just looking at this standard normal score. Again, we're going to go to get the normal CDF, we're going to go to second vars for the distribution menu and then select normal CDF. If you are on the classic mode or you're using an older calculator, then you will have to remember to enter a lower bound, an upper bound, and then the mean and the standard deviation separated by commas. If you're in the stat wizard mode, you'll get a screen that looks like this, and it will remind you what you need to enter and in what order. So we're going to specify negative E99 here. So the E key is just like a power key for 10 to the whatever. In this case, this is going to mean 10 to the 99th power. So it's essentially the equivalent of infinity. On your calculator screen, the E command is actually above the comma. So you would hit second and then the comma to get to that E function if you're typing it. Now, above the comma, it says EE, but I think that's just there to distinguish it from the letter E, which is the key above it with the alpha menu. So EE is that exponential E that stands for times 10 to the power. And so you would type the negative key, not the minus key, but the negative key, then your second comma to get the E, and then 99. That's equivalent of our negative infinity. And then comma up to where we're stopping would be the 1.35 z-score, 0 for the mean, 1 for the standard deviation. And we can do the same thing here. The 1 in front of the E is optional. Sometimes these numbers are filled in by default, and that's fine. You can, if it already says -1 E99, you can leave it there. Again, the z-score in this example, since we're calculating less than that, would be the upper bound. And then the default, if you leave these out in the old version of the calculator, they will default to 0 and 1, but they will appear on the screen here so that you can confirm that is in fact what you want. When you hit paste, this command is going to show up on your screen, and then hit enter. So let's look at a second example. Now, the age of employees at a manufacturing plant are normally distributed with a mean of 45 years and a standard deviation of 12 years. An employee is stopped at random and asked to fill out a questionnaire. What is the probability that the employee is between 35 and 55 years old? So again, we want the area between these two values on our normal curve. The mean was specified to be 45, the standard deviation of 12. So if we were typing this out by hand, again, you would go to your distribution menu, second vars, scroll down to normal CDF, and then you would enter your lower bound of 35, comma, your upper bound of 55, comma, your mean of 12, comma, your standard deviation, so your mean of 45, comma, your standard deviation of 12. In the stat wizard mode, again, you will just fill out the values. Again, same order, 35, 55, 45, 12, and then again, hit paste. It will put this on the screen, and then it will calculate your probability for you. Let's look at one more example. The weight of third graders is normally distributed with a mean of 60 pounds and a standard deviation of 4 pounds. What is the probability that a third grader weighs more than 55 pounds? So 55 is the smallest number of pounds, and we want to go all the way to infinity. Anybody bigger than that? Again, it's best to put these in. I mean, smaller numbers will often work fine, but if you get into the habit of using E99 in place of infinity, this will be the most consistent results. Sometimes, depending on the size of your standard deviation and the value of your mean, you may want bigger and bigger endpoints. And if you just use E99, you won't have to worry about what would be big enough. So our lower bound is 55. Again, our upper bound is now E99. And again, that E is above the comma, and it means times 10 to the. So this is a 1 with 99 zeros after it. It's basically the biggest number that the calculator can handle. And then 60 is our mean, and 4 is our standard deviation. And then again, if you hit paste with the wizard, this will pop up on the screen. And then you could hit enter to calculate your probability. Now, we can also use this to calculate things like confidence intervals, although there is a function in the calculator to calculate confidence intervals, so you don't need to do this. But we're going to go through an example of calculating the probabilities for various values of a sample. So in this example, we're going to calculate the standard deviation of the sample, the standard of the sampling distribution. And for problems involving means, that's going to be the standard deviation over the square root of n. And again, this is just going to be the probability that you collect a sample that is more or less than a particular average value. So this is akin to our sampling distributions, more like our confidence interval cases. This is kind of an intermediate case where we're calculating probabilities, but we're calculating them from the sampling distribution and not the regular distribution for an individual observation. So let's look at how this differs. So the weight of third graders is normally distributed with a mean of 60 pounds, standard deviation of 4. That's the same as before, but this is now asking the probability that a sample of 40 third graders will have a mean weight less than 58 pounds. So notice we're taking a sample of 40 of them, And so since we're dealing with a sample and not an individual child, that's when we're going to convert our standard deviation to not just 4, but 4 divided by the square root of our sample size. So inside of our formula, we want less than 58. So the lower bound will be negative E99. The upper bound will be 58. The mean is still 60. But again, the thing that's important here that changes is that because we're dealing with a sample of 40, the standard deviation will be 4 divided by the square root of 40. And again, you don't have to calculate this as a decimal and then enter it in the decimal. You can just type in the expression like this. I think there probably should be one more closed parentheses here, but the TI is a little bit more forgiving than some calculators on forgetting to close the probability. Forgetting to close parentheses at the end. In the middle, it hates it, but at the end, it's a little bit more forgiving. It's like, I think you meant to close these. Now, in scientific notation, this answer comes out to be this. Remember, this E stands for times 10 to the, and then whatever follows it is a power. So this is 7.828 times 10 to the negative 4. 10 to the negative 4 means there are 3 zeros after the decimal place before you get to the 7. So this is very small. When you're calculating probabilities, students far too frequently will forget this number at the end, and they will think, oh, it's 7.8. 7.8 is not a possible probability. That should be a giveaway that this is not a traditional decimal. This is in scientific notation. And it's probably a very, very small number. Remember, probabilities have to be between 0 and 1. And so 7 is not even conceivable. Now, another alternative that we want to worry about is if we have the percentile value or the percentage, and we want to convert that to either a standard score or an observation value. Now, in this case, we're going to use the inverse norm function in order to convert back, essentially to do the problems we were doing before, but in reverse. So we know the probability and what is the score that's giving us that outcome. So this inverse function can also be found in the distribution menu. So again, select second vars to get to the distribution menu, and then inverse norm is right below that, which is number 3. Enter the cumulative area, and then again, the percentage, the percentile score below that, the accumulated area, and then the mean and the standard deviation. Typically, if you don't specify the mean and the standard deviation, it will assume 0 and 1. Particularly in the older versions, even if you don't type them, in the newer version with a stat wizard, it may assume your previous values. So it's better to make sure that you fill them in as intended. So here we want to calculate the z-score for P90, which is the 90th percentile. So we would specify 0.9, again, as a decimal, and then 0 and 1 for our mean and standard deviation. With the stat wizard, it's going to look like this. When you hit paste, you're going to get this same thing on the screen. And then when you hit enter, the z-score is 1.282. Now, newer calculators will have an inverse for the t distribution as well, not just the t PDF and CDF. The t is going to work very similarly to the normal distribution, but you will need a degrees of freedom and you will have no mean and standard deviation. But the inverse function doesn't exist on older calculators, so you can see that it's missing here. On the newer calculators, it does exist. And so, it will work somewhat similarly to these. Now, we only generally use the t distribution in hypothesis tests and confidence intervals. And so I'm not going to make a separate video for the t distribution, at least not right at this minute. It's not on it's not on the agenda right now. But you will encounter the t distribution in other contexts, particularly confidence intervals and hypothesis testing, and we won't really use these distribution functions in this menu, sort of separate from that context. And then finally, our last example, we have the life of a GE electric fan is normally distributed with a mean of 4 years and a standard deviation of 1.2 years. The manufacturer will replace any fan free of charge if it is under guarantee. For how many years should a GE fan be guaranteed if the manufacturer does not want to replace more than 5% of them? So 5% of them, we want that area under the curve. So essentially we're saying we only want to replace the bottom 5%, the fans that won't last that long. So that bottom tail, not the top tail. So we're going to put the 5% in here for our probability. If we were saying doing the top 5%, then it would be 0.95. So we'd have to do 1 minus that. So here our mean is 4, our standard deviation is 1.2. And again, on the stat wizard screen, we will enter it again in that same order, and it will remind us what all the things are for. And then when you hit paste, it will give you this on the screen, and then you hit enter. And again, because you've entered a mean that is not 0 and a standard deviation that is not 1, this is a year's value. So it's not a standard score, it's an actual number of years, which is the units that our mean is in. So in this case, GE should guarantee the fan for basically 2 years or around 24 months. And then beyond that, if it lasts longer, great. If not, but we're only warranting those 5% of fans that fail sooner than they should.